Okay, so hi everyone. Before we get started, I want to give you some context. Within the advent of our community, one theme repeatedly comes up. We are all taught to model and to have some kind of smart algorithms for optimization problems, but almost nobody is taught to build optimization systems that last. That's the gap between theoretical OR and real world operations research. And it's the gap this interview aims to explore. So today I'm joined by someone who understands that gap better than almost everyone I've met. He's Tim Varelmann. Tim Varelmann is one of the clearest modern voices at the intersection of algebraic modeling, high quality software engineering, and industrial OR practice. He's the founder of Bluebird Optimization, a consultancy and training company helping teams build maintainable, scalable optimization systems. And he studied computational engineering science at the Technical University of Aachen, University of Queensland, MIT, and UT Austin, and has worked with leading European companies like Zalando and SAP, plus startups from Germany to Silicon Valley. So thanks, Tim, for being here with all of us today.
My pleasure.
Well, looking at your company, what you share on LinkedIn and your course, I feel you have a philosophy I'd like you to uncover today with all of us. So this year's Advent of War focuses on the whole life cycle of optimization projects. Where do you see the biggest gaps in how professionals move from model to adoption?
I think the reality of software is that it changes often. And even if it's already in production, it's not done once, going to production, and that's it. And in the generic software world that's not specifically focused on optimization, there was this movement of continuous integration and continuous deployment that sort of produced some infrastructure for making changes often, and continuous deployment also supports making changes if the thing is already in production, of course. I think Next Move is a company that has a platform that really brings this over to the world of optimization very well. But yeah, when software changes, and that's really the reason why it's called software, not hardware, back in those days when these terms were made, let's say. We have some options to already make our lives easier before we go into production. And that's just when we design the model, when we design the software. And software is just easy to change when it has a bunch of good properties that make it high quality software. For starters, it's easy to read. If software is easy to read, then it's easy to give this to other people, to bring in new experts, stuff like that. Therefore, that always makes your life easier and just gives you more flexibility to work on the software if a change is needed. Just general ideas of maintainability. If you need to do some extensions, extendability, you do some things and now you want to add a different flavor of it. How easy is that to do? That's a change. And if you've done the software development right from the beginning, then that extension should be easy to add. In particular, it shouldn't change anything from the things that are already existing. Tests are also something that, again, coming from continuous integration, help a lot to ensure that whatever we already have maintains correct, and to also ensure that what we build new is doing the things it's supposed to do correctly. So yeah, testability is also a quality of good software, because if it's easy to write tests, then you will write tests and then your software will be tested, and that's good software.
Well, that's pretty insightful. I think you've covered pretty much all the engineering stuff regarding the life cycle of optimization projects, and that's pretty good. Let's talk about a bit deeper on the engineering side, because this is what I see where several operations research projects might struggle. So you often talk about separating data from equations, and I would like to understand why is this so impactful, and maybe what other specific software engineering practices do you consider essential for an optimization model to remain maintainable over time, apart from having tests?
Separation of concerns is the easiest, the quickest bang for the buck if you're just starting out to improve your software quality. And if you separate equations from data, you have a very clear line how to separate them. If you watch at a line of code, it should be pretty obvious to determine, is that something that should be in the data section or that should be in the equation section. In other cases, software engineering is a bit of a science, but also a bit of an art. And when things get more difficult, the art part is more prevalent in the tasks that we have to solve as software developers. But when you start with separation of concerns by separating data from constraint logic or general optimization logic, that's easy to do in the beginning, and therefore it's a quick win that already cleans up your software a lot. That's why I make this statement very often, because it just helps people get the first momentum going. And I guess in the world of optimization, algebraic modeling in general is a principle, a concept that makes this easy for many of the other more intricate things as well. I think algebraic modeling is just a fancy term. In my opinion, it should be called set-based modeling. That's what we would call it if we would coin the term today, let's say, because what really is going on in algebraic modeling is that you define sets and you exploit these sets, and that makes your software easy to change. So if we have a look at, let's say, route optimization, right, Bora, you work at Trucksters. I did some projects in the past as well, as you mentioned. We can define a set of trucks. We can maybe also define a set of drivers. And then later on in the section where we deal with optimization logic, we can say, hey, each truck has some skill. Maybe it has a cooling capacity, and that cooling capacity may be 0 if it's just not available. And maybe we have some trucks that have a lot of cooling capacity and some trucks that have a little of cooling capacity. So we can put all of this in parameters. But now if our model changes, we have a new truck, you just add that truck to the set of trucks. And now your parameter will, of course, require a new set of data as well. But the amount of changes that you have to make are very little, because all of the constraints you have are typically defined over the set of all trucks. So you don't really have to change anything in that logic part anymore.
That's pretty interesting. And I can see there are two main topics in what you have just said. The first one is the more artistic part of engineering side. And the other one is algebraic modeling. So we are going to cover each of those in the next following questions. You've also shown that engineering and modeling reinforce each other, and I feel that modeling is also something more like artistic. You need to have some art in there, and I know because you've written an article recently where you refactored like 2,500 lines into just 48 using algebraic principles. So what were the key ideas behind that transformation? What modeling patterns do you wish more practitioners understood earlier because of that knowledge that you had because of that?
Yeah, I mean, that was, of course, the pinnacle, right? When you have a very bad starting point and then you have a very nice way of getting a good result, then you achieve these great transformations. In general, I think modeling, and that refers to the art part of it, I think modeling is a translation process, really. So that it's a communication task, and therefore it's not so much hard science, but more something soft, which is this communication thing. It's important when you do modeling anywhere you go to talk to everybody involved. That's when I start a new project, the first thing I do, and spend almost a week just making sure everybody who's involved gets spoken to. They might not really in the first week have anything valuable or any requests for me at that moment, but it's still important, if only just for the sole reason to build trust, that everybody is heard. And yeah, of course, it opens the communication channels for later on, because you will also iterate when you build a model. A superpower I could recommend is using suitable visualizations, right? The suitable part is important, because you can also do visualizations that are just confusing. But if you have suitable visualizations and then you iterate with people who are not from the optimization world, but know their domain in whatever business we are working in, that's sort of the translation, again, happening from the model to the people, so that you can show what the model is currently doing. And that gets their creative juices flowing a bit to tell you more constraints. Because if you just put people down and say, hey, here, write on a piece of paper all of the constraints, all of the requirements you have, that will never be complete in the beginning. But what works a lot better is just, hey, let's start with some constraints or some requirements that you have and that you can formulate. And if you forget something, that doesn't matter, because we will iterate a couple of times anyways. And I will show you what the model is currently doing. And that will make it easy for you to detect, hey, there's something that we don't do like this, or we don't like it, we want to avoid it. Can we please change that? And yeah, it's a translation process, both starting in the beginning, taking requirements into the model, and then iterating back from the model to the current results to close the loop, essentially, and also close or complete the amount of requirements that people have.
So I see this is kind of an iterative way of building a solution for a business, right? It is like, okay, so we start with something that might be small, but then after having conversations with different stakeholders and understanding better the business needs, then you incorporate that information into the model and in order to give better solutions to business, right? You've been talking about algebraic modeling, and I would like to dive a bit on that because it's them that sits at the core of your work. And you argue that algebraic modeling enforces good engineering naturally. What makes it so powerful, apart from the set-based modeling that you've just talked about? Which features do you think, like dynamic sets or vectorization or lead-lag operators, do you think they are still undervalued in industry? Do you think maybe we need to promote them more? What's the overall arc around algebraic modeling? So what do you think is what makes algebraic modeling powerful? Those kind of features that algebraic modeling will give you or will give practitioners, like the most powerful part of it.
I think it's really hard to pinpoint one component of algebraic modeling because really it's just an entire concept that is just well rounded and well thought out. And so if you do the entire thing correctly, then yeah, you have a framework that guides you naturally to writing high quality software. And all of these bells and whistles that we have in algebraic modeling, you mentioned like maybe there's lead and lag operators and stuff like that. They are just there because the real world requires them. So that's very problem specific. If you're working with time series, you're probably looking forward to using the lead and lag operators of algebraic modeling. And because algebraic modeling is such a well-rounded out concept, of course, you can also do lead or lag by not just one time step, but multiple time steps if you ever need that for some reason, right? So all of that is possible, but I think it's just, yeah, you get what you need to model real world problems. And the idea of high quality software is somewhat intangible, whereas algebraic modeling really gives you, for people who have an engineering mindset, who say, hey, I need a clear list of things to do, just steps that are a lot more actionable. And I think that's the power of algebraic modeling.
Yes, and I think it's like the real powerness of algebraic modeling from the more engineering side. So I would like to get a bit more personal here because in the end you work a lot with algebraic modeling. Was there any point in your career that was like an aha moment in which you said, okay, this algebraic modeling thing is something that I need to push further and start doing it in every project that I tackle?
I think the biggest revelation was just in the beginning when I first heard about algebraic modeling and saw it in action, and it was immediately clear how valuable it was. I personally had a lot more development on the software engineering theory side, let's say, to do. That happened later on. But whenever I came back to using algebraic modeling, or I mean, it was the other way around. I knew algebraic modeling, and then I made some more leaps forward in the software engineering theory. And whenever I had some new theory learned, I could already see how this is already done in the concept of algebraic modeling. So it was just reinforced over time, I would say.
And you've worked with both giants like Zalando and small startups. What modeling lessons applies equally across these very different worlds?
I would go back to the translation process thing because it doesn't matter how big a company is, if it's a giant corporation or it's a small startup with a couple of techies. Modeling is a translation process, and you have to understand that it's not about the math of the software you write, but about the communication, because that's where the value is, what makes the model valuable in the end and usable for those who want to use it.
So yeah, the communication part with stakeholders is one of the keys to a successful project in the end, right?
Yeah, and it doesn't change regardless of how big or small the company is that you're applying this to.
Pretty insightful. So now let's talk about GAMSPy specifically because it sits at the intersection of modeling and engineering, and specifically with the algebraic modeling. How do you explain the value of the Python syntax plus GAMS performance to someone who's only used open source tools, for example?
That's a big topic. So GAMS is obviously a commercial tool for doing algebraic modeling. And the biggest difference between commercial tools and open source ones is the performance, because performance is what makes these commercial tools commercially viable. That's what I hear from GAMS. That's what I also hear from Gurobi. And both of these have been around for decades, right? Gurobi, not as Gurobi, but the founders who gave Gu, Ro, and B, the name to Gurobi, they worked at Cplex before, and Cplex existed for decades. So you get the idea that the thing entirely exists since several decades as a commercial one already. And in fact, that's what you always hear when you talk to people, why commercial options are viable for them. It's because we really need the performance and we can't just wait for anything to happen. And there's also a reason that makes it easy to understand why these commercial tools are better in terms of their performance. They really have dealing with sparsity figured out. At least for algebraic modeling, right? Gurobi does also all kinds of other stuff for the algorithmic stuff. But when we look at algebraic modeling, what GAMS does and what also other commercial competitors of GAMS do, maybe they have less experience than GAMS, but they really deal with sparsity well. So if we go back to the example with our trucks, then we might just have a couple of trucks that have cooling capacity at all. And most of the trucks, if you have a fleet of 100 trucks, don't have any cooling capacity at all, so it will just be zero. It doesn't make sense to compute a lot of things with zero, because everything you multiply with whatever, so if you have a multiplication of zero and it's something else, it doesn't matter what that something else is, the result will always be zero. So you can save a lot of computation by just saying, hey, this thing that we are multiplying with zero afterwards, we just don't compute it in the first place. And propagating this properly takes decades of experience, but GAMS, for example, has it and does it really, really well. How we deal with sparsity and therefore the amount of computations you have to do, the amount of data you have to communicate is just a lot smaller. And yeah, you can really see that difference when you compare GAMS, for example, to Pyomo, where it's most striking, but also Julia does it a bit better than Pyomo, but still Julia, or I think it's called JUMP, like the open source algebraic modeling package of Julia is called JUMP. And if you compare JUMP to GAMS, there's also still orders of magnitudes different between them.
Tim, I see you have a lot of experience. You are giving a lot of insights, and I see a teacher inside of you. You built a course, and your course has become a reference for modern modeling, specifically using algebraic modeling. You say your course teaches in 10 hours what took you 10 years to learn. So what are those 10 years of lessons, and what motivated you to package them the way you did it?
My goal was to really have a well thought out order of teaching things that just works with suitable real world examples. I think when you want to learn something the fastest, it happens when you have a real example to apply these principles to. So ideally, you already have an optimization problem in your company, and then whatever you learn that is new to you, you can already have a look at this specific application here, where you have stakes, where you can make money or at least make somebody else's life easier, and apply this immediately and have an impact. That just makes all of this learning process so rewarding, and that would really accelerate the learning process. So I really made a point, first of all, thinking through the order in which I want to teach in this course, but also making sure that I have suitable real-world examples. And when it comes to examples, I personally have a bit of a bone to pick with the Python culture. So here it goes. I think the Python culture, when we have a look at documentation, so you read the docs for some library, and this applies to all of the libraries. It's whether it's NumPy, Pandas, Matplotlib, in GAMSPy itself, it's true as well, right? People at GAMS do a lot of amazing work, but this is a trap they also fell into. When you look at the documentation, the examples you find, they are the simplest examples you could possibly imagine. If you have an interface where there are any additional parameters you could put into a function, but they have some default values, you never see these as an example. And what I often happen, maybe just because I like to work at the boundary of what's possible, I want to combine two different non-default values for some parameters that have default values, and I can find nothing at all in these documentations. And like it's really important to understand how these two non-default parameters might interact with each other. And it's just not well documented what this behavior will be. And I think that's just bad. And I get the idea that we want to simplify things, specifically in teaching. But I would really accuse the Python culture of taking it one step too far. They stopped simplifying and they've taken it one step too far and started dumbing things down. And I didn't want to do that in my course. So what I did is I took the general level of examples that we have and increased the difficulty of these examples by one step again, because I think that's a proper way of simplifying things, but not dumbing them down, so that these examples are still something where you can really learn something from. You can use them to teach valuable insights that go beyond just the standard plain vanilla version of using these things. Yeah, wow. So that ended up in quite a rant. But I guess if that happened in Python, really, for example, also vibe coding would have been a lot easier. If it were documented how these things interact with each other, then a lot of stupid things that ChatGPT or stuff like them they do, if they had read it already in their training, they wouldn't do these stupid things, right? So there's a lot of even long-term implications of this, and that's my take.
I really like that approach of simplicity, but with real life problems, with real life examples, because in the end, that's the thing that will teach the most to students, right? I find a lot of value on that part. So I would like to start wrapping up this interview. So let's bring things back to the advent of OR just for a moment and the community learning experience overall. So if you have to say just one, what's one modeling or engineering principle that could dramatically improve the results of everyone going through the advent this year?
So I have a technical and a personal idea. Let's start with the personal one. I would say dare to be more disagreeable. I mean, what just happened was you saw me essentially accusing the entire Python environment. For me, it's easy to say dare to be more disagreeable because I am more on the disagreeable side in terms of personality already. But in a technical environment, I think it's easy to be disagreeable if you do it right, because it's not about personality per se, but just about being prepared better than the average of people are prepared. So be prepared well when you go into a meeting. If for some reason you haven't prepared a meeting and then in a meeting there are some decisions made and later on turns out you have like a bit of a feeling this would not be the ideal decision, bring it up. You need to prepare then and make a case for why this decision you made in that meeting was not so good and there is a better alternative, obviously. But people have good intentions. And if you approach people with valid criticism and give a better alternative, typically they will very much like that. And if they really don't, then you're probably working with the wrong people. And it's also good to find that out early on. So in both cases, whether you're working with good people or with bad people, it's good to find out. And just being more disagreeable in a constructive way would help you. And then we have already talked about separation of concerns as a technical component. I think the ideal state of software is that every component really has just one reason to change. And if I say component, I mean that on a level of lines of code, but I also mean that on a, like, let's say a module of a software, and also the entire software is one thing itself. Obviously, the one reason why this entire software should change is a bigger reason than why one particular line of code should change. And again, this is the thing between art and science. This is an ideal that you can't always achieve in software engineering, but you should strive for it. And just asking these questions, what is the one thing that should trigger a change in this component of the software, will lead you to write better software, first of all. Because when you ask questions, you sometimes find the answer. Sometimes you may not find the answer, but still thinking about it, make sure that you leverage your own potential. If you're just starting and you're in your second year of being a developer, you're not as senior as some architect who has 2 decades of experience, and they have seen a lot more patterns with a lot more detail, and they can answer these questions. So if you ask these questions and you don't have an answer yourself, I would say take them to some more senior people and just bring up the question, because they will also, again, be very happy to answer them. You can learn something in the process. And if they don't know the answer, then at least they probably understand that it will be very important to focus more on it, and that you can sort of be the spark for directing attention into the right direction with this. So that would be my take, I guess.
Tim, this was brilliant. Seriously, I really enjoyed this conversation. Do you want to add anything else on top of everything that you have said?
I'm pretty good, I guess. Stay in optimization. It's an awesome world, and just, yeah, stay with us.
So thanks for joining us today and for helping the OR community level up its engineering and modeling mindset. Thank you very much, Tim, for being with us today.
It was great. Thank you.